Third session of this engineering section. So in this session we have two moderators, Professor Swarnendu Sen and Dr. Aditya Saurabh. So I would like to give the brief introduction of our moderators. So Dr. Swarnendu Sen is a professor in Mechanical Engineering Department at Jadavpur University. He did his graduation, master's and doctoral degree from Jadavpur University. He is a fellow of several societies including DAAD, International Society of Energy, Environment and Sustainability, and Bengal Academy of Science and Technology. His area of interest includes heat transfer, reacting and multi-phase flow. He has authored more than 200 research papers in different international journals and conferences. The second moderator of this session, Dr. Aditya Saurabh. So Dr. Aditya Saurabh joined IIT Kanpur as assistant professor in 2019 and recently is working mainly in the area of thermoacoustic instability, liquid jet atomization, combustion noise, active and passive acoustic damping in gas turbine and hub. So with this introduction, I would like to hand over this session to moderator Dr. Swarnendu Sen.
Very good morning to all of you. Thanks to the organizer for a nice introduction. So I will request my co-moderator, Dr. Aditya Saurabh, to introduce the session first.
Yes. Hello everyone, clearly. Can I get a response? Hello?
You are not audible, Aditya. Please switch off your mirror so that bandwidth can be improved.
Can you hear me?
Unmute your mic.
Can you hear me? Hello?
Maybe you can start.
Okay, I think there is some technical steps, so let me introduce the session. The session is on coal biomass combustion for power generation. So we all know that coal is one of the most important in India and also for the world. So its efficient utilization is critical for sustainable growth and development. And sustainable growth and development is also dependent on the development of novel alternative sources for power generation. So among the various new and upcoming strategies, biomass for power is among the most promising. So that is basically the background of this particular session. So we have 6 panel members in this session who will introduce their views first. So let me introduce our panel members. So our first speaker will be Professor K.K. Pant. Professor Pant is Petrotech Chair Professor in the Department of Chemical Engineering at IIT Delhi. So he has received his BTech in Chemical Engineering from HBTI and then his Masters and PhD from IIT Kanpur. Professor Pant is adjunct faculty in the University of Saskatchewan, honorary faculty of University of Queensland, joint faculty in the Center for Rural Development at IIT Delhi. So he is also presently holding an administrative position. He is fellow of several academies. To name a few is INAE, National Academy of Science, Royal Society of Chemistry. So his expertise is in many areas, and one of them is biomass conversion. So after Professor Pant, our second speaker will be Professor Shantanu Dey, who is from Mechanical Engineering Department, IIT Kanpur. He received his bachelor from North Bengal University and then MTech from IIT Kanpur and his PhD from IIC Bangalore. Applies to a transformative industrial practice. His focus is the development of a world-leading research capability in heat recovery and energy storage. So our fourth speaker will be Professor Amitabh Datta from Power Engineering Department, Jadavpur University. He will be our second online speaker. So Dr. Datta is a professor in the Department of Power Engineering in Jadavpur University. He completed his graduate education in Mechanical Engineering from Jadavpur University and his PhD from IIT Kharagpur. Dr. Datta is a recipient of Alexander von Humboldt Fellowship. He is a fellow of INA and also our society. His research interest includes combustion, atomization, energy, thermodynamic modeling, and application of CFD in reactant flows, and also microfluidics and biological flows. Our fifth speaker will be one eminent engineer from industry, Dr. P.A. Lakshminarayan. He is currently an advisor to Simpson Engines, Chennai. He developed models for heat release and emissions for diesel engines based on the study of fuel air mixing at the valve in turbulent sprays with multiple injections. He also studied the wear of liners having a general surface texture and tribology of valves, cams, pistons and rings, and there are many other accolades in his name. I just named a few. And our sixth speaker will be Professor Omkar Singh. He is a founder vice chancellor of Madan Mohan Malviya University of Technology. So he did his bachelor from HBTI, TU, and then his master's and doctorate also in mechanical engineering. He is a professor of mechanical engineering in HBTU since January 2007, and he has also been vice chancellor of Uttar Pradesh Technical University. He has authored 10 books, 9 book chapters, 223 papers, and he has guided 13 PhDs. So, and he has received a lot of awards in his name. So with this very brief introduction, I will request our first speaker, Dr. K.K. Pant, to start his speech, and I will request all our speakers to restrict their speech by 8 minutes so that we can have a good time for our discussion and question and answer session. Thank you.
Good morning, all of you, and Thank you, Professor Krishna Sen and Vitat for introducing me. I hope I am audible, right? Yeah. So since this is a very short interaction for discussion, so I have just made a couple of slides to give the overview of what is required to be done in terms of the coal gasification. So this is what you see. Now most of the time when you look at the coal gasification is only for the power generation. But now if you look at the trends in terms of the scenario, when the ministry has decided to go coal to hydrogen. And coal to hydrogen, when you say coal is a dirty material, and converting coal, which is full of carbon into hydrogen, definitely is a challenge, And everybody has to look at that. In what way, how the hydrogen can be extracted, and definitely it's not a green hydrogen. So we need to look at how this hydrogen can be made clean hydrogen. So there are a couple of understanding or thoughts have been given. What you see here, the theme with carbon management. So everybody talks about carbon capture, storage and transfer, So that's what how to coal gasify, convert it into syngas, and followed by a water gas shift reaction, and then you can talk about how the carbon dioxide can be captured, efficiently either store it and then use it for some other power. So those things are very challenging, and these are need to be addressed with respect to what you see here, the energy security. That's energy security, and then economic advantage and environmental benefit. But as I said, Indian coal is not of high quality; it's a highly ash, 40% ash. So how to handle those kind of ash, is very challenging. The second is one of the another point which you see here, 163 billion tons of this coal reserves are already proven out of this 344 billion tons. So India has limited natural gas reserves, So natural gas is relatively cleaner, but reserves are limited. So we have to still work, and that's why the COP26 said phase down, not a phase out. So we need to work accordingly, And 18%, if you look at more coal would be needed if you convert. That is the demand of hydrogen, and that is 1/3 of the transportation demand. So hydrogen is considered as a clean fuel, and everybody is talking about green hydrogen. But green hydrogen, if you look at by water splitting, is still very costly. $6 to $7 per kg of hydrogen, which is not economical for the Indian scenario. We need to get hydrogen at least at the rate of say 150 to 160 rupees per kg, and that makes more and more challenging. You should see here, what we do. This is a kind of typical process when you talk about the coal and you gasify it, It can be oxygen, That is what the oxygen gasification, air gasification, And then you have the raw gas. So raw gas now depends on this oxygen, water, how much is added. You can have some combinations of the hydrogen, CO, CO2. So most of the time it varies from 14% CO, 14% hydrogen. It can go to the level of 26% CO2, 26% hydrogen. So those things are still challenging, and you have to now, we are looking at kind of concept that is already Niti Aayog has decided, coal to methanol. So that also makes a sense that you can have this, compress it, and then you can have the methanol synthesis. I'm not discussing that part. If you look at the coal gasification part, for power generation versus the syngas conversion and finally to methanol or any other power fuel stocks. So you see here that the typical temperature range is around 900 to 1000 degrees centigrade. So that is the different kind of gasifiers are in commercial market. But when you look at the Indian scenario with 40% ash, there are again a lot of challenges in order to handle this kind of Indian coal, and you have a lot of equity like hydrogen sulfide, ammonia, carbonate sulfide. How do they affect the catalysis is also very important. So a couple of R&D is still needed because most of the time what we do, most of the high pressure gasification systems, these are between say 4 to 5 bars, If you go to 10 bars, it may be more efficient, but there are a lot of issues with that. So a lot of HPTG analysis with connected with mass spectrometry, because the tar formation, all these things are to be done. So these are a couple of, you see that effect of pressure, effect of temperature, 850 degrees centigrade, you are trying to work at. When you talk about the combination of exothermicity and endothermicity, you need to again look at a different concept of this. So these are the couple of R&D activities which is to be done with respect to the different kind of coal, And that can give you the correct picture about the, what pressure, what temperature, and how the conditions can be optimized. And these things are still at R&D level with respect to Indian scenario. And most of these technologies are in the hand of like Shell and multinational companies, not Indian. So we are doing a couple of understanding, right? With thermites, we have done this kind of what you call optimized gasifier, which is basically oxygen gasification of this. But you see here, right, when you talk about these conditions, how these right the gasifier is designed, what is the height, what kind of right structure should be there, the coal feeding, what size of the coal, all these hydrodynamic studies are very important. And then there is a cyclone 1, and then this is directly down from the this can be said, because most of these gasifiers have the efficiency of 90%, but remaining 10% is again right to be converted or sent it back in order to do the efficiency. So these are a couple of right. One can do the Aspen analysis, and more importantly, do the exergy analysis nowadays, not just from the simple mass and energy balance, but need to do the exergy analysis and get more and more energy into the system to make the entire process more and more economical. So lots of modeling studies are being done, and that is need of the future. So as I said, that exergy analysis and simultaneously you need to do the process intensification, right? And this is kind, right? How to miniaturize of these kind of units? How can you split the these and get the energy? And this is the process to be clean. So all these utilities should be captured here. And finally, so you need to have high temperature set, low temperature set to get the maximum hydrogen which can be absorbed 99.9% pure, and that can be used for the regular applications. Right? So, but that's what I said, right? You need to find the way how this type of catalyst can be used for a system. So, another issue is that because coal is a dirty material and India has plenty of availability of the biomass, so then you can have a co-firing of coal and biomass also. So, can coal and biomass be mixed together? That could be like one of the options, but it has been observed that when coal and biomass are mixed, you need to tune the ratio of the coal and biomass, and that is what mentions here. Because of the paucity of time, I'm not going in detail of this, but the entire picture looks like this, and all these things are still to be done with respect to Indian scenario. So we did a lot of these kind of economy analysis, because what cost, at what rate the power will be obtained. So those things are very important. So you see here, when you have a biomass, so biomass you can have oxygen and air, and with this you can have syngas, you cool it. So your biomass tar is much more like denser than the coal tar, right? So that's again a challenge, that how to get rid of this tar. So there are a couple of tar reforming systems, and then you have the entire process stream which can be done, and finally hydrogen can be obtained from this, and here the syngas can be separated, and directly syngas can also be used for the gas turbine systems. So this coal to ethanol is another option when you have the syngas, and that can be taken. But again, you see that there are a lot of challenges in this process. Development of the catalysis, right? So with respect to the concept of VTI utilization of 40% S, so we are working jointly with Thermite with the support of Department of Science and Technology, and we are developing this 1 TPD local coal to methanol plant in the country. And finally, the idea is that 100 TPD and 1500 TPD of coal to methanol plant will be set up in the country when this notion plant gets success. So, economy analysis is very important, which is to be done. So you see that with the coal and biomass, then if you have the Rankine cycle, the efficiency is poor, which is just 35%. So it is to be improved. If you have IGCC, efficiency is 43%. So with this, you see that 4.47 kg coal or 0.57 kg of biomass for every kilowatt hour of energy equivalent is required. But when you have the IGCC, which is 43%, then only 0.838 kg of the coal or 0.46 kg of the biomass for every kilowatt hour of energy equivalent can be used. So this is very important, that how to address all the challenges and get the economy in this. So just because of the shortage of time, this is the initiation of the process of discussion. So you see that there are a lot of conclusions and way forward when you look at the Indian highest code and how this can be utilized efficiently, and then it can be this gas can be used for combined cycle power plant to generate electrical energy. Efficiency with respect to Rankine cycle, so the Rankine cycle efficiency is poor, so we need to improve this. Then you see the carbon capture, gasification technology. This is 60%, while this is just 35%. So we need to work on all these stuff. If you look really to utilize the Indian great coal for syngas and power, hydrogen is another option. You can reform it and you can have hydrogen. And from here, because hydrogen storage, right, is still an issue. Vehicular application is still an issue. So we are looking for these two can be converted into methanol, which is hydrogen to carbon ratio 4:1, and much better for the vehicular application. So with this, just I conclude here, and thank you very much for your patience.
Thank you, Professor Pant. So our next speaker will be Dr. Shantanu Dey.
Good morning, everyone, and thanks for giving me the opportunity to present this and discuss the future of the coal and biomass utilization. So, this topic I think Professor Pant has nicely introduced, and I do not need to ponder over there. So, coal is the primary source of our energy, and we, the global perspective or we in the Indian perspective, and we are using a significant amount of coal for our energy worldwide, and that is also causing a huge CO2 emission. So we need to see that how we can make it better, as Professor summarized that. And now, if you look into the Indian scenario, we are using about 50% and higher about coal for our use for the power generation. Right? And in the growth rate of this coal, you see that it is more or less now it is about 50 odd percent that much coal we are using for the power generation in India. So can we do something better? As most of the coal that we have, they have a very high ash content, and typically in the range of 30 to 50% in that range. Therefore, the utilization becomes challenging. So how we can make the coal clean and use it for our benefit? So that is why these clean coal technologies are being talked about. So one of the technology, the IGCC, and then there could be other chemical synthesis plants that can be, depend on this coal as the feedstock. And also there is the fuel cell application. So for all these things, we need to have a gasification plant where we can gasify the coal and use this, whatever the product necessary for the downstream applications. Right? So in this process, we can also try to capture some of the CO2 in some of the processes. But again, capturing CO2 will incur some loss of efficiency. But ultimately, we should probably move towards that. And this is the combined cycle power plant using a gasifier, and that Professor Pant just now discussed. So I'm not going into the much details about this, but that there can be different types of gasifiers for gasification of coal or biomass. Some of them are listed here. So fixed bed gasifiers, and they are basically very simple in construction. And here you can introduce the feedstock from the top, and there can be two types of that: updraft gasifier and the downdraft gasifier. Usually the particle size we are not bothered about much. It's very large particle can be fed, and then you can get the synthetic gas from this. And the typical temperature within this bed varies. So this can be about 1000 degrees centigrade and higher, and there is a non-uniform temperature distribution within this. Another type of gasifier which is mostly suitable for low ash coal is basically the ingredient flow gasifier, where we can have an operating temperature of 1400 degrees centigrade. And if the ash content is more, then again it becomes problematic to use. So therefore, this ingredient flow gasifier is almost ruled out for high ash coal that is available in India. So what we can do, we can use basically another type of gasifier, that is a fluidized bed gasifier. And here you can have a uniform bed temperature within the gasifier, and then you can convert the coal into the synthetic gas. And then depending on the different operation, there can be bubbling fluidized bed and circulating fluidized bed. And one of the concepts is also the dual fluidized bed. So these are they offer fuel flexibility and a uniform operation of the bed. And the particle size is typically smaller particle size. Now, there could be two different types of operation. One is the autothermal gasification, where basically you are sending an amount of air in, as a fluidizing media, but and you are burning some of the solid fuel in situ, and you are producing the thermal energy required to sustain the gasification. So that is the autothermal operation. And in this process, since you are sending air, if you send air, there will be a lot of nitrogen dilution, and the produced syngas will have a low calorific value. So, and then it will become difficult to use it for the downstream applications. So, what can be done? We can replace air by O2 using an oxygen plant, but again, it increases a lot of costs. Another approach is basically the dual fluidized bed concept, where we can achieve allothermal gasification, basically by separating two reactors, one for the combustion, another for the gasification, and then the circulating bed material. So this bed material will basically carry the heat from the combustion to the gasifier, and then the endothermic gasification reaction can be sustained. And you can also some part of the feedstock can be burned in the combustion. So in this process, you avoid nitrogen dilution because in the gasifier you can give steam, and then here basically C plus H2 is going to CO plus H2, and you do not have any nitrogen in the right. So that is a good option, and you can achieve a medium calorific value syngas formula. So now some of the recent developments that took place in India, having the government aims to have about 100 metric ton coal gasification by 2030. So there is a lot of scope, and there are many areas where we can work, like the apart from IGCC, the synthetic natural gas, or the urea for the fertilizer, etc. JSPL recently set up a gasification unit, and that is basically for the steel, basically the direct reduced iron plant. And the BHEL also has come up with a fluidized bed gasification technology for highest Indian coal, and that is capable of producing syngas. But nevertheless, the research cannot stop here. I mean, we can try to improve this efficiency, when we can try to achieve the different other objectives. I will outline some of them towards the end of this. So we have also done a humble beginning at IIT Kanpur. So we have made a gasifier setup. So presently we are operated a public fluidized bed gasifier, and we gasified the highest coal, which is having about 45% ash. And we face some certain challenges that I will introduce. So there are some, I will help you work on the highest coal gasification in autothermal reactors. And mostly you can see that the ash percentage is about 40% or all. And recently we have done gasification of 45% ash coal, right, in the BMP configuration using air and steam as the gasification. So our outcome is basically here, and we achieved some of these parameters, like the carbon conversion efficiency is about 71 to 85%, which is in line with other reported ones. But of course, the high rating value is having about this much, about 2 to 3 megajoule per normal meter cube. And we face certain challenges due to the formation of the alloy. Okay, we observe that if sometimes the particles can settle down, the largest particle can settle down in the gasifier, and locally there can be a fixed bed kind of situation, and then the fluidization stops. So forms clinker because of the local hotspot. These ash particles can fuse, and then they can grow in size, and it can lead to defluidization. So we have investigated the composition of this fused ash agglomerate, and we have seen that there are some alkali metals and alkali earth metals which are present in the feedstock, can form low melting point eutectics. So these are some certain challenges that we need to address somehow, and to make it possible. So in my opinion, the directions of the future research are that dual fluidized bed gasification, if we can do, we can achieve medium calorific syngas for the downstream application by avoiding nitrogen dilution, and the hot gas training of syngas can be one of the direction using inexpensive catalysts, or we can use another technique like plasma upgradation of syngas. Of course, Professor Pant said that pressurized gasification, and that is also quite needed, because there are downstream applications where you basically synthesize different chemicals. There the pressurized operation can be beneficial. Another approach could be that, like from the production of hydrogen, that oxygen separation membrane, we can work into that direction, where we can get high purity of oxygen, high purity of hydrogen from this membrane reactants. So these are some of the directions in my opinion. And thank you for your attention.
Thank you, Dr. Dev. So our next speaker will be Dr. Kumar Pachigola, who will be presenting online.
Am I sharing the slides? Yeah, okay. Okay, good morning all. Now I'm going to talk about biomass co-firing. This is another dimension to what KK Pant and Dr. Santanu talk about coal gasification and the biomass gasification. This is another approach can be done to meet the carbon emissions targets requirement globally. So next slide, please. So to start with, this is the pathways towards zero emission reduction targets we set here in UK couple of years back as a part of Advanced Power Generation Technology Forum. There are three options at the time we considered. Now it came up with more of other options as well. The top in that list is first one is like a carbon capture and storage that meets a lot of carbon reduction approaches like 90% up to, and co-firing will come into the picture to meet the reduction targets, and then followed with an efficiency gain. When and how long it is, then we put them into a near term, medium term, and long term approaches. However, these scenarios has been changed in the UK context. However, this can be easily applied and linked to the other countries, in particularly in the Indian context as well. Next slide, please. So in terms of this biomass utilization in the power generation, what are the main drivers? What implications it will have? So it's particularly this biomass, either it could be waste energy crops, which can be used that will automatically reduce the carbon emissions from your coal power generation sectors. This will give an opportunity to get maximum energy recovery from that biomass rather than using it for conventional food stoves and all those things. So lots of energies will be wasted. By utilizing this co-firing approach, that maximum energy can be recovered through the use of high efficiency coal plants. Again, the efficiency of the coal plants, we are talking about 30 to 40%. Along with that, Santanu clearly mentioned about the corrosion problems, agglomeration, and those things. So co-firing with the coal will avoid these issues, in particularly biomass on its own. Along with that, low sulfur content of the biomass leads to reduce the sulfur emissions from your high ash and high sulfur coal content, so that meets the environmental and air quality regulation point of view. Don't forget, along with that, last but not the least, the market opportunity of these co-firing do exist globally, where coal is used for electric power generation. That is what I did notice. I think Santanu clearly showed that the energy mix in India is pretty much 52% of power generation is coming from the coal. By adding the biomass will provide these reductions and the benefits, and it will give a good market opportunity. Next slide, please. So what are the concepts? What are the options? Do we need to replace the full coal power generation one, and what type of approaches we need to do that? There are several approaches biomass co-firing can be done, like either direct or indirect approaches. If it comes to the direct co-firing approach, that means indirectly mixing the biomass with the coal in the fuel handling system, So that means you need to pulverize pre-treatment. You need to do that, pulverize that biomass and mix it with the coal in that coal belts before it goes into the burners. And you don't need like a separate fuel system, but you need the handling system so that there won't be any impact on the conventional approaches. When it comes to the indirect one, that is particularly like gasification approaches, can be linked to gas-fired power plants at later stage. If not, you can do that in parallel and connect it to the power block onwards, like means steam generation, and use that one for steam approaches. On the bottom right hand side gives you where the biomass has been applied globally and what are those numbers in particularly. It is part of that IEM, International Energy Agency Bioenergy program, picked up the relevant programs where the biomass is heavily used in the power generation sector. Next slide, please. So in terms of biomass co-firing, just a few examples of the types of biomass we in UK normally use it. Muscanthus, it is a high energy, that means a high calorific value, high energy crop. We normally use that one in power generation sector. And the willow wood chip is also commonly used in the system, and we got access to all world trade coals and biomass available in UK. Next slide, please. So what are the issues if we use a biomass into the system? It's the current issues, it's the quality of the biomass, flexibility pre-treatment, and increasing the co-firing is a cost effective and it meets the environmental constraints, as I mentioned. Along with, there will be a technical barriers. What are those? Like insufficient mixing will end up with the impact onto the boiler, chloride corrosion and those things, alkali corrosion, some of the aspects Santanu has mentioned it. And the ash coming from this process, unburned carbon, utilizing in cement and other road making approaches, what impact it will have. Along with that, because of the biomass usage, there will be a negative impact onto the downstream process like selective catalytic reduction or through flue gas desulfurization. How this co-firing is happening, just a snapshot kind of thing at one of the UK power plant, Tilbury. As you can see that on top of coal, the pulverized biomass is sprinkled so that goes into fuel system. Next slide, please. This is the important slide. You all need to know that and what we are doing in here in UK. So the top is the grid watch, which is equivalent to energy mix. What is our demand and how that demand is met? Most of our energy right now, 50% is coming from the renewables, either wind or solar, and still biomass is playing a reasonable role in coal power plants. What is the scenario for the UK's coal plants? Most of our coal plants is a shut right now as we speak. 4 coal plants is running in UK, but they are at to shut by 2025. Our target is to reduce the emissions, going to the more renewables, but still those 4 power plants doing co-firing approaches. Next slide, please. So what is the UK perspective to the Indian perspective? In the UK point of view, we are using these co-firing approaches, the knowledge is there, and we applied it to the more power generation sector. So Indian perspective, for my understanding, co-firing is yet to be established, mixing coal with biomass, need to introduce carbon neutral fuels, and its biomass is available in India, and innovative R&D is still underway, mixing with coal. Next slide, please. So as a summary, I don't want to go far more into the UK context. That is what I have mentioned, but at the bottom, what is the current status in India? Just a quick snapshot kind of thing. If I'm correct, the total biomass in this installed capacity is roughly about 10 gigawatts, which is majorly talking about biomass on its own. It has a potential, biomass potential in India. Current availability is, based on my information, around 750 million metric tons per year, which is equivalent to extra 28 gigawatts of energy, a huge amount. Along with that, there are plenty of sugar mills is available. Sugarcane bagasse can be used to produce the electricity either in its own form or a co-fired approach that can give an additional 14 gigawatts kind of thing. So I got a few pictures kind of thing. Next slide, please. Just to give you an overview of how the handling systems is happening in UK versus some developing countries. As you can see that on the right hand side, it's shredding and drying is happening naturally, and it got a lot of losses you will end up with, and contamination into the lands and pollution issues. Next slide, please. And this is about the transportation, cost-effective transport systems approach, to give you a brief overview about what is happening across both regions. Thank you.
Thank you very much. Our next speaker will be Professor Amita Balapta.
Good morning. Can you hear me? Hello?
Yes.
Am I audible?
Yes.
Okay. So at the outset, I would like to thank the organizers for giving me the opportunity to speak on this occasion. And thanks to my friend Professor Sen for introducing me to the audience. The topic that I have chosen is use of biomass in Indian power sector. And I think this is a good follow-up to the earlier speeches that we had in this session. Next slide, please. If we look at the power sector, we see that the energy and the electricity sector in India has seen a very rapid growth, particularly since the last decade of the last century. And this is evident in the bar diagram that we have on the left. Presently, the installed capacity in the country is about 392 gigawatt, out of which, as already pointed out by Shantanu, 53% is coal. There is 27% renewables, 12% hydro, and 2% nuclear. So together, the non-fossil fuel contribution is about 41%. Out of the renewables, we have a large solar installation over the last couple of years or so. At present, 47% of the renewables is from solar, while wind, which was till few years back was the highest, is presently having 38%. Biomass power generation, as already pointed out by Dr. Kumar, is about 10 gigawatt, and that contributes 10%. So next slide, please. At the same time, India is very much committed towards sustainability and has taken pledge to reduce the carbon in the atmosphere, though the per capita carbon dioxide emission of the country is much less compared to some of the developed countries like USA and Canada. Still, in recent years, the government of India has taken the pledge to reduce the emission intensity of its GDP by 33 to 35% of the 2005 levels, and to have installed capacity of 40% from the non-fossil fuels, which, as I have shown, has already been achieved because we are now having 41% from non-fossil generation. But if next slide, please. To achieve this target, the government of India had made a target of having 175 gigawatt of renewable installation by 2022, out of which 100 gigawatt is from solar and 10 gigawatt from biomass, which has already been reached. So this was the target, but then under the reduced scenario, if there is 150 gigawatt installation, then out of that 80 will be from solar, and if it is 125, then 60 gigawatt will be from solar. But these are regarding the installation. If we consider the generation from the renewables as against the installation, and then if we look at the two figures on the right, we see that the generation percentage is not at the same rate as that of the installation. The recent figure shows that though installation of renewables is 27%, the generation in 2019-20 is only 10%. This is mainly because of the variability in solar and wind power. We cannot have a regular supply of solar, and it depends on nature to a great extent. So to this point, the renewable sources are vulnerable, and this is where the biomass can fill up the gap to a great extent, because such vulnerability will not be there in case of biomass, as we have some steady supply from different routes, may it be woody biomass or agricultural crop or whatever. So taking this into account, the government of India has taken a new policy of introducing biomass co-firing in the existing coal-based thermal power plants. Next slide, please. So the policy, which was introduced in November 2017, has been revised in October 2021, that is very recently, and it says that the coal-fired power plants in the country will have to use 5% blends of biomass pellets, primarily from agro residue. And this they have to do within 1 year from the time when this guideline has been introduced. And then it is further said that within the next 2 years, this percentage share of biomass has to be increased to 7%. So for bowl mills, it has been said that the agro residue biomass can be directly used, while for other type of mills, ball and race mill or tube ball mill, torrefied biomass pellets are to be used. So after torrefication, that pellets are to be created, developed, and used in case of ball and race mill and tube ball mill. India, as has already been said, has abundant agro residue, and it is estimated to be 230 million metric ton from agricultural residues. But the implementation of these policies are yet to be started in most of the plants that we have in the country, and many of the power plants are still very apprehensive for several technical reasons.
I think we can move on to the next.
Yeah, I think we can move on to our next speaker. So, Dr. Lakshmi.
Good morning. Thank you for the opportunity. I just bent and twisted the title the organization given to me to my taste. I will talk about a case for bio-CNG buses for a city like Chennai. Daily, the waste collection is increasing, and the map shows how yearly it is rising from around 4,700 to 5,900 tons in a matter of 2 years. There, in the city, only LPG is available. We don't have many networks, but recently there are 25 mineral CNG stations placed in the city. But the CNG buses are completely absent in a city like Chennai. We have noisy diesel buses of yesteryears. Electrical buses are a fad now, but they are about 3 times costlier. Advanced CNG vehicles are already in the market. For example, by Ashok Leyland, Mahindra, and Tata. If you see the status of waste collection in the city, you have ordinary compost, vermicompost. I mean, they are to different scales, multiplied by 10, biogas, etc. We can convert this waste to biogas and compress that to a very high pressure, create bottles of CNG, bio-CNG, and feed it to the industries and automobiles. 30% of the solid waste is biodegradable. With the new techniques, instead of 30 days, we are able to convert to methane in a matter of 15 days. For example, 1 ton of biodegradable waste from the city can produce around 30 kg of methane and 150 kg of carbon dioxide, 50 kg of organic manure, etc. But organic manure and methane have value. In the city, there have been proposals and then pilot plants, 5 pilot plants built already in the last 5 years. There in a very smaller scale, you need around 300 square foot of land per 1 ton of treating garbage every day. And what is important is the residents must segregate the waste for the project to be successful. So in some areas where we have population which is a bit compliant, such plants are made. And these plants are using bark technology from Bombay. The total feeding capacity is 8.8 metric tons of biodegradable waste. They produce around 54 kilowatt hour per day of electrical energy just for demonstration purposes. It's not very economical, but still we don't collect this nuisance methane in the atmosphere, and at the same time we produce some fertilizers. But it gives us a lot of confidence of producing useful energy, useful energy as well as fertilizer from the waste. Now, this is a typical biogas plant. I will come to that in the next slide later. There are 2 types. One is you feed the muck in the conveyor and then feed it to the digesters and create methane and convert it to compressed natural gas. The other is to fill it in the land and extract the gas from the landfill, which is practiced in some of the European countries. And in India, we dump it and that emits a lot of methane into the atmosphere and pollutes the air. So here also we can extract methane, but it's a bit more organization is needed compared to what we are showing in the top. So there are many bio-CNG plants in India, and here this is the one which is there in Chennai at Mahindra Research Valley, and that produces around 500 kg per day. There are bigger plants in Maharashtra, Gujarat, and Rajasthan as per this table. So you see a functioning plant in the city. It is working for the last 5 years, I think. You dump the biodegradable input from the city. It is a very organized city in the outskirts of Chennai. Then that is converted to biogas and fertilizer in the primary digester. Then you have a secondary digester. And most importantly, the gas contains about 18% carbon dioxide, which must be removed. Otherwise, it becomes very difficult to make it as a useful automobile fuel. So all the carbon dioxide is removed. And the next most important thing is we must remove hydrogen sulfide, which produces rotten smell. But more problematic will be the corrosion of engine parts. So completely desulfurization is done. Then we have to compress it to 240 bar, and it is available at 98% pure grade bio-CNG, which is better than the mineral CNG, which is around 95 or 94% at the best methane number. Okay, this is a high grade CNG, and this can be delivered at the pump outlet for running vehicles. So if you see the calculations, it's very interesting. It shows here per day how much muck we produce in a city like Chennai, and you can extract so much of methane from that in the 15 days. Normally we have around 260 kilometers per day of distance covered by the buses per bus. And we have around 3,100 buses in the city. If you can use this methane completely in the CNG buses, we can run 830 buses essentially free. But there are other hidden costs. For example, we have to create an infrastructure. You have to collect the muck. You have to also you make some money by selling fertilizers. The cost economics works out with the volume of the biogas plant. If you work out in terms of the metric tons or meter cube per hour you produce, you get a decent cost of around 45 rupees per cubic meter when you have large plant. It shows we can have 2 large plants for a city, big city like Chennai, and then run around 800 buses only on CNG. Okay, it is not mineral CNG, so it is everything anymore. We have tractors, for example. You have buses already running on CNG, so there is no need to have a new design, and they produce very little emissions. And you work out the economics of all this, and the payback period for new buses is within 3 years. After that, you run all the way to the bank and make money by selling on diesel. So it's environmentally friendly. You get some byproducts. Combustion is very, very clean compared to diesel. And one of the biggest headaches we have for diesel engine is maintaining DPF on the road, especially in cities. And there is no DPF for CNG. It's highly sustainable because we keep producing garbage every day. Vehicles are highly noiseless compared to diesel, and we have payback in 3 years. We have examples elsewhere. For example, in Norway, they have many buses by MAN. I think with this, I will conclude my presentation. Thank you very much.
Thank you, sir. Thank you. So, let's move on to Professor Omkar Singh.
So, my presentation is on biomass-based combined power and heating systems. A lot of discussion has already been there about the biomass, its availability, its conversion. Now it's on its utilization for the power generation in particular. If you look at the global scenario, it's more than 1/3 of the global electricity which is still coming from the low carbon sources, but a lot less of total energy does come from it. So this statistics is giving you some idea about the electricity generation from the coal, gas, nuclear, hydropower, and wind, and it's only 2.5% from the other renewables, which includes everything. But if you look at the total energy scenario, that is oil is at 3.1% and coal 27% and so on. So that's how this statement becomes relevant, that more than 1/3 of the global electricity comes from low carbon sources, but a lot less of the total energy does come from it. This is about the installed electricity generation capacity. Previous speaker has already covered this particular aspect. But if you look into the percentage, around 60% is from the fossil fuel and 40% is from the non-fossil fuel. So, if you look into the target which we have set around 40% electricity generation from renewable energy by 2030. But by October 2020, the installation has reached 89.63%, which is only 24% of the total installed capacity of the country. Similarly, if you look at the fuel-wise generation capacity, there also the biomass power and cogeneration is only 2.6%. But looking upon the availability of the biomass and the prospects which it offers, there is a lot of opportunity. So we should think for coming up with the new power plants which run on this biomass. Maybe it's not individually with this biomass, we can have a combination. So, this, if you talk of the electricity generation concerns in particular, the requirement is constantly increasing. So one of the aspects could be, let us meet the increasing electricity requirement by improving energy efficiency of the existing plants or set up new plants. So the first one is very relevant because if we tap the wastage which is happening, probably we can contribute significantly to the total electricity generation. In contributing, another aspect is contributing decarbonizing the electricity generation by adopting low carbon generation options and renewable energy. In view of the climate change concerns, this becomes much more relevant. If you look into the combined heat and power, this graphics will give some idea how the systems can be. We can have internal combustion engine, then diesel engine and gas turbine. In external combustion sector, we can have steam turbine, we can have stirring engine, we can have Galena cycle, we can have organic Rankine cycle, and in no combustion sector, we can have fuel cells. So it's a great potential which it is offering. If you look into the biomass, the classification is one important aspect which I don't want to go into the details. The classification, again, if you talk in terms of the India, as per a report, it says it's 500 million metric tons, which has already been shared, and 150 megawatt equivalent gasification plants on or off grid are there, and the global bioenergy plant capacity is 140 gigawatts. So we have potential and we need to do a lot in it. Similarly, if you look into the biomass classification, it can be one go to syngas, another is syngas with high hydrogen. So this is useful for electricity generation. We can use it for gas turbine and fuel cells and thus generate electricity. This is again a biomass-based power generation. So we can have gasifier, we can have followed by gas filter, then scrubber, then condenser, and then we can have engine generator. Another option can be we can have your IC engine here, then we can use its flue gas for the purpose, then we can have the gas turbine attached to it and we can use the syngas directly into it, or we can have fuel cells. This is giving you idea about the biomass classification integrated with solid oxide fuel cell. So we can have this syngas coming and hydrogen coming from it, which can be used in solid oxide fuel cells that will be offering us power, and whatever is available as waste that can be used for heat. So fuel cell, solid oxide fuel cell is the best choice because it offers, it's better from the corrosion perspective and the electrolyte loss perspective. Then if you look into the power to gas technology, hydrogen is again offering a great potential. It helps in decarbonization because the challenge is low cost, low carbon hydrogen production. That's the challenge of the day. This hydrogen becomes a clean fuel because it does not give you pollutants to the extent which we are getting from the present options. Then producing hydrogen via electrolysis using renewable energy is possible. Oxygen produced as a byproduct in water electrolyzer can be used for oxy-fuel combustion in gas turbines. And this is again going to improve the plant efficiency to a significant level. This oxy-fuel combustion, if you look in particular, this uses pure oxygen, which offers high economic and environmental value. So the possibility of using low-grade fuel is there, less nitrous oxide, NOx generation is lesser, and ease of carbon dioxide capture. So this is one graphics which is giving idea about how the biomass can be used, and then we will be getting, whatever exhaust we are getting, we can use it in a steam cycle, that is Rankine cycle. And if we still have the exhaust available, we can put it in an organic Rankine cycle or the Galena cycle. So this is an indicative calculations which we have done that Brayton cycle efficiency is coming out to 47%. Slide as you see. It's okay. So this is which I wanted to focus that we can also go for the integration of the solar and biomass integrated combined power and hydrogen generation plant. So solar energy can be used for biomass classification. The syngas which we are generating that can be used for gas turbine cycle. Then the exhaust can be used for steam turbine, and whatever wastage we are getting that can be used for low temperature cycle, that is organic Rankine cycle. And its exhaust can be used for electrolysis purpose, and we can get the hydrogen And the oxygen which we are getting, that can be further utilized, and that can be utilized for oxy-fuel combustion. So a bigger combination can be thought of. So this is the schematic which is giving idea about it. So this is the solar tower. Then we have a gasifier. Then we have a syngas coming. We are using it for the combustion to get the working fluid for gas turbine. Then the exhaust is sent to the heat recovery steam generator. Then the steam turbine is contributing in the power output. Then whatever we get, that is being sent to the organic Rankine cycle. That's low-grade energy which we are getting, that is over here. Again, power augmentation is there. Then we can send it for the electrolysis and get the hydrogen which can be stored. And the oxygen which we are getting, that can be sent back to the combustion chamber for oxy-fuel combustion to the extent it is possible. So the power output contribution which we could get, that was around 72.5% from gas turbine, this is the 4.8% from organic Rankine cycle, and 22.7% from steam. The efficiency wise, this is this much. Then the barriers, there are a lot of barriers since time is I think it's over, but I can quickly rush through it. It's inconsistent properties of biomass, then operational problems are there, which make gasification technological deficient, then uncertainty in the biomass supply pricing, it is there, then limitation of the gasifier is there, and high initial cost and reluctant financing system. So biomass integrated power and heating system holds potential as the environment-friendly polygen options. However, economic viability in terms of cost competitiveness with fossil fuel plays a critical role in its implementation. So I will be closing with the let me conclude that the greatest threat to our planet is the belief that someone else will save it, whether it is the energy availability, climate change, or the damage which we are doing to the environment. We do not inherit that from our ancestors, rather we borrow it from our children. So everybody should work for protecting the climate, increasing the availability, energy availability, and the electricity generation, which is the core of the present civilization. So thank you very much.
Thank you, Professor Singh. So we can spend 2 more minutes to complete Professor Datta's talk, and then we can go for the question and answer session. Am I audible, Professor Datta?
Can you hear me?
Professor Datta, can you hear me?
Can you hear me? Can you hear me?
Yes. Yes.
Okay. So if we go to the, I'm very sorry for the technical snag. Yes, if we go to this slide. So what we were talking is that the government of India introduced a policy and revised that only a couple of months back to introduce biomass co-firing, and this is direct co-firing of biomass to the extent of 5% along with coal. But the implementation of this has not yet been started, and the power plants are still very apprehensive because of several technical reasons. If you go to the next slide, please. The technical issues are the availability of uniform quality of biomass all around the year and across the country. Then the torrefaction plants, it has been said that torrefied biomass will be used for certain types of mills, but there are not enough torrefaction plants. Torrefaction is mild pyrolysis at a temperature of 200 to 300 degrees centigrade to remove some volatile matter from the biomass, because biomass contains a lot of volatile matter as compared to that of coal. Then transportation is also an issue. Biomass being of low density requires a large volume, and that's why it requires a large transportation cost, and therefore they are going for pelletization of biomass in order to reduce the transportation cost. But the two important issues for which the power plants are particularly apprehensive are the fuel preparation and the combustion issues. In terms of fuel preparation, they are not very certain whether they can get rid of mill fire. As the Indian coal contains a relatively high percentage moisture, about 10% or so, often the power plants have to run their coal mills with a relatively high temperature of air. So at the exit of the mill, the temperature can even be around 90 degrees centigrade or so. And they are apprehensive whether at that temperature the biomass, if it is given in the mill, can catch fire or not. Now, controlling the mill temperature therefore becomes a very important issue for the power plants if they have to use direct co-firing of biomass. The other issue is the combustion issue, where they're not very certain about the stability of the flame, or particularly about the deposition of ash, considering the fact that the biomass ash contains alkali metal, and as a result of which the ash fusion temperature is relatively low. On the other hand, the Indian coal contains relatively low volatile matter, and therefore many a times the power plants have to maintain high furnace temperature in order to burn the coal. So they are not very certain whether that high temperature of the furnace will result in slagging due to the low ash fusion temperature of coal of biomass ash. So these are the issues regarding which the power plants in practice they are still thinking over, and therefore they are also thinking over whether to go for parallel co-firing instead of direct co-firing to reach the target. Next slide, please. In this context, the distributed generation with the help of biomass can be an alternative. We now have in our country grid fed electricity supply, but in distributed generation, it actually pertains to low capacity, a few kilowatt. Next, please. Few kilowatt to about 10 megawatt, small capacity plants. Next slide. Yes, connected to the system, and then it can either be grid connected or islanded with small capacity power plants. And it has been, next slide please. It has been shown that in such distributed generation, biomass gasifier with gas engine can generate electricity at an economic rate compared to many other alternatives like PV or wind turbines. Next slide please. But there again have certain issues. We all know that fixed bed gasifiers using biomass coupled with internal combustion engine is a developed technology, but the issues are regarding cleaning of the producer gas generated as a result of it, like removal of tar and particulates. The other important issues is the handling of multiple feedstock. You cannot expect in a distributed generation to have the same feedstock over the year, and if the feedstock changes with the change in the components of the feedstock, there you have to make certain adjustment. That adjustment can be the adjustment of the feed rate, adjustment of the equivalence ratio, and you have to develop a strategy so that you can generate producer gas at the same rate over the year with different feedstock. And we did a study on this, and we also did a study of blending feedstock, like blending of woody biomass with animal dung to use as a fuel in gasifier for the generation of electricity in a distributed manner. Furthermore, there has to be a proper policy for acquiring feedstock over the years, because it has been found in many places that due to non-availability of such a policy, it becomes difficult for the plants to acquire feedstock uniformly as is required for the plant over the whole year. So that is another important issue that has to be considered. Then we can also have gas turbine based power generation using external firing, and we also did a study on this. We can talk on this if we have time. Next slide please. So coming to the conclusion, India is committed to climate change initiatives, and the government is taking active measures to help in mitigating carbon emission. And to meet this, biomass is being considered as a suitable fuel, considering the abundant availability of it, and policy has been taken to introduce biomass co-firing with coal. But there are various technical issues which are to be met, and because of which the power plants are still apprehensive regarding implementation of biomass co-firing in practice. Distributed generation in this case can be an alternative with tremendous scope and opportunity, and we can think of it instead of only thinking regarding biomass co-firing in centralized power stations. So thank you very much. Thank you for your patient hearing and giving me the opportunity.
Thank you, Professor Datta. So with now our session will be open for question answers. So we can take question from the audience.
Good afternoon. It's a question from Professor K.K. First of all, I congratulate everyone for a very nice lecture, which was full of good information and practicality of the things. So my question is that you talked about poor quality coal and then like converting this into hydrogen. How does poor quality coal affect quality of hydrogen?
Thank you for the question. Actually, see, the coal gasification is still a challenge. And when you look at the highest coal and the quality of the Indian coal, right? So, when you talk about the syngas production, it depends on the production of that is how much oxygen, how much air, or how much steam has been used. Now you have to make a combination, right? Highly exothermic versus endothermic, or a combination of these two. So you need to adjust the hydrogen to CO ratio in the final syngas. Now, as I said, that syngas, right, which is a mixture mainly of hydrogen plus carbon monoxide, but when you are doing this process, you have the carbon dioxide also. So typically 10 to 15% is the carbon dioxide, 14 to 15% of hydrogen and CO combination. But if you have the efficient gasifier, like I said, oxy-steam gasification, by that process you can reach to a level of 25% of hydrogen to CO. So good quality of this CO, syngas, CO and hydrogen, that affects your final performance in terms of the energy, right? Because you are trading off between the water gas shift reaction. So water gas shift reaction is something where you have a CO and hydrogen. Because most of the coal gasification plant, if you see the syngas, the hydrogen to CO ratio is less than 0.5. And this kind of hydrogen to CO ratio is not at all accepted nowadays. So you need to improve this hydrogen to CO ratio. And that's why either steam, use the steam. So steam will partly help in terms of carbon steam gasification reaction and tar reforming reaction. So with that you can improve your hydrogen to CO ratio in the final product. That is one thing. Second thing is that, as I said, the clinker formation. So now gasification temperature is also very important. So most of the gasifier, like ability gasifiers, right, these are good for the lowest. But for highest coal, where the India is also trying now, most of these gasifiers are presently bubbling bed gasifiers. The efficiency can be enhanced further, say 90% conversion efficiency can be taken to 95 if you have a kind of real fluidized bed gasifier. But design of this kind of real fluidized bed gasifiers are still quite a challenge and at R&D level. So 1 TPD, 5 TPD or 50, 25 TPD, these kind of plants are on operation. A lot of work is being done. So this quality of the syngas with respect to hydrogen CO ratio is very important. We talk about the hydrogen. And then followed by water gas shift, high temperature or shift, low temperature shift, you can tune the hydrogen maximum. Thank you.
Sir, what was the difference between good quality hydrogen and poor quality hydrogen?
See, this depends on the, because I said that it is a mixture of hydrogen plus CO. And now you have to use the water gas shift reaction. And that will give you CO plus H2O reaction, will give you hydrogen. So what is the maximum hydrogen present in your product, end product? That is important. So definitely you need to have the carbon dioxide capture in between. And finally to reach to a level of, say, PSA, to reach a level of 99.9% pure hydrogen. That is required.
Thank you.
question in this regard to Professor Pant?
It was a very good session actually. So my question is, any of the panelists can answer. It is open to all of you. So, when we look at this classification or co-pyrolysis of coal and biomass, we all know that the main problem comes the huge difference of the volatile matters, and that's what it affects not only the conditions but also the reactor designing, because it's completely into extreme. So why can't we look more on? I know that also we have to work in that case to have sustainable technologies for making chars. But why can't we look more for co-gasification or co-pyrolysis, together co-gasification to make good quality syngas, so that we have a good control for liquid fuels downstream on char and coal instead of biomass and coal. Because even though I don't work more on the gasification, more on the pyrolysis side, but from my experience, I feel this could be one of the, if we can get a good quality char, it can, because biomass has less ash, so these char and the coal together will solve many other problems of this volatility and volatile matters difference, and that can be looked through policies. And also, since biomass has low ash, so even if the coal-based has more ash, it can be taken care. But it will give a benefit of this reactor designing and taking care of. And one more benefit which I could see, that it will be easier to control the HC ratio. Whether we want to go for the DME or methanol or there, the ratio, we can play better there if it is char and coal than biomass and coal. So just to comment on this.
Yeah, thank you for your question. And again, this is very important. In fact, see, you must have heard in my presentation, I stressed that coal plus biomass is very difficult to gasify together, right? So my suggestion would be to gasify them separately, because biomass tar is still a challenge, much more challenge than the coal tar. So you need to look at how these two conditions can be optimized. Right? So my suggestion would be that you gasify coal separately, biomass separately, right, and run these two in parallel, because ultimate aim is that you are moving towards some kind of green sustainable, right, or a kind of green energy. So with coal and biomass, you cannot reach to a level of green energy, but adding biomass, say 5%, which one of the presenters are also said, right, that can make a combination of a kind of towards green and sustainable mobility, where the biomass can be utilized. That is the first part. Second part, I still stress, because that is again a challenge, whether you should go coal, right, gasification, that is of course a lot of gasifiers are there, but for biomass still pyrolysis is another option. You convert it right into liquid fuel and then reform and then reach to a level of biomass to hydrogen. Because there the approaches are different, energy consumption is definitely important. So if one can look at this approach of plasma gasification or plasma pyrolysis, but through exergy analysis, because you need to avoid a lot of duty operations in between, then only this plasma process can be economical. Otherwise, presently the plasma gasification is 60 times costlier than the biomass or that simply thermal or thermocatalytic gasification. One more thing which is to be added now is introduction of the catalyst into the system. So potassium carbonate, like Reliance is now doing, right, petro gasification using the potassium carbonate as a catalyst. You can improve the hydrogen to CO ratio to 5:1. That's what they're doing, right? So those kind of things are to be done, and a lot of R&D is required in order to maintain this hydrogen to CO. And then, if possible, if you want to move towards hydrogen, or if you want to use it for methanol or carbon dioxide hydrogenation, that is to right 1 or 3:1 hydrogen to CO or CO2 ratio, or combined CO plus CO2 combination can also be used for converting these carbon into the chemicals. So that's again a petrochemical concept, where all these can be utilized and you can capture the carbon and convert it into value-added chemicals. Thank you.
Yeah, I mean, Professor Pant has nicely summarized that. I just want to add that, I mean, whatever Dr. Das probably was saying, I think we can add this. After pyrolysis, whatever the char is remaining, we can mix it with the high ash coal, and that will solve some of the problem of the high ash that is available in our coal. and then this charge can be also burned in a dual fluid as mode, and then we can transfer the heat to the the gasifier to sustain the thermal reaction concept. So that can also be a subject of study. And before doing that, I think that we can study the synergy between the coal and this coke actually, the charge basically. And after that, we can probably move into that direction. Yeah, it is a nice direction, and I appreciate it. Thank you.
So, any supplement from our online speakers? Okay. So, any other question?
I have no question. So, my work is mainly combustion and power, but I have curiosity to know that for gasification we require gasifier.
Please raise your microphone. It is not audible.
Actually, my work is more on combustion and fuel, but I have curiosity to know that for gasification we require gasifiers that mainly run on electricity. And then how efficient is this to convert waste to valuable feedstock through gasifiers that run on electricity, and maximum electricity comes from the coal in India. And the second question, that is there any possibility to convert waste to valuable feedstock through solar assisted gasification, like with concentrated solar power? Is this possible to raise the temperature up to the limit at which the gasifiers?
Okay, so regarding the electricity from consumption in the gasifier, I think there is no direct electricity that is required for the gasifier. Whatever we discussed about the autothermal operation, there you burn a part of the feedstock in situ in the gasifier, and that will create the thermal energy to sustain the exothermic gas emission reactions. So we really do not require any electricity to sustain gasification. And coming to your second comment, that is the solar assisted gasification, I think there is some work in that direction. Our IT friend from our IIT Mandi group, they are trying to do something on that solar assisted gasification, and it can be, it may not be possible to take that temperature to up to that whatever the temperature that is needed for gasification, about 800 to 900 degrees centigrade. But what can be done? We can produce steam from this solar energy, and that can be used in the gasification reactions during the gasification process. So it can offset that steam generation cost or something like that, and that can increase the process efficiency.
So there was a question from Dr. Alok.
Thank you. This is the general question. Any or many of the panelists can give. In India we are now talking about completely moving away from coal biomass combustion and moving towards solar electricity by 2070, long range plan 50 years from now. So does anyone among the panelists think that is it really technically feasible, or is it something that is really going to happen, or it's just talk in the air to satisfy the global climate watchdogs?
Whatever understanding I have, I don't find it to be feasible, because we do not have resource energies can replace these two. And the robustness of the technology which we expect to be a substitute for it will take its own time and its own course. And there are a lot of initiatives being taken pertaining to the fuel cells, hydrogen as a fuel, but still they are all in infancy, and 2070, maybe even beyond that, the complete substitution of this coal and coal in particular and biomass in addition to it may not be feasible. That's my take on it.
I can just add a little bit, say, let us be hopeful, right, instead of going a little bit on the negative side. But of course, this is a challenge, right? The solar assisted, as I said, presently the cost is a major factor. And it's a $3 to $5 right, per kg of hydrogen versus what we are looking in India now, 120 to 150 rupees per kg of hydrogen. And that is what the target of coal to hydrogen, RDF to hydrogen, biomass to hydrogen. If the cost comes within the range of 120 to 150, that's I think the most of the I think one of the solutions for the country. But solar assisted, definitely, since there are a lot of challenges with solar assisted, but I think in the future, if you are able to draw down the cost to a level of like 150, I think that is possible, practically possible. It will take time, but we cannot, because we have plenty of coal reserves available, and natural gas, right, is not available for this. But if you look at in terms of environmental sustainability, government is also planning to shut down a couple of coal gasification plants, power generation plants because of the pollution. So we need to look at the improved design of these kind of gasifiers, assisted with solar plus hybrid. So I will say that this should be a hybrid system, partly solar energy, partly maybe electrical or steam, look at the other sources like natural gas also, whatever available. Then definitely there will be a solution and gradually phase down and then phase up. So it will take time, but it will come out. Some solution will be there.
So, Doctor, any supplement from your side? Please unmute yourself.
Yes, I have unmuted myself. Can you hear me now?
Yes, sir, we can hear you.
Okay. So, just a comment to the previous question regarding volatility of coal and biomass. And it is the reason for which torrefaction is introduced for biomass. That helps in reducing the volatile percentage present in the biomass. Now the question, if you talk about firing biomass along with char, by removing the complete volatile matter from the coal, then probably that will not be a very good idea considering the stability of the flame, because the volatile matter present in coal also helps in stabilizing the flame by its good burning and feeding back the heat to the char to take it to the ignition temperature. So that will again be a challenge, and you have to think of combustion strategy by which you can burn char along with volatile matter, along with biomass in a steady flame. Probably with 5% biomass, it will be very difficult because you will not have enough volatile matter to stabilize the flame, to give it a good ignitability. So that is one point. Regarding this particular question, whether it is possible to go to entirely solar, I also agree with the other panelists that in near future it may not be possible because of the sole reason that the variability of solar power does not help in giving steady supply to the grid. And for doing that, you have to have a lot of energy storage. That will again introduce a lot of cost to the system. So probably for some years from now, we will have coal in the system unless we have a generation of hydrogen, as Professor Pont mentioned, good quality hydrogen in sufficient quantity to generate power. So till that time, we have to depend on coal for generation of electricity.
Can I add something here?
Please unmute yourself. Can you hear me? Please unmute yourself. Okay, any other questions from the audience?
I have a question on there's a new fuel which is coming up, ammonia, which is raising a lot of interest as a green fuel. So how do you see the future of ammonia in various industrial applications?
Yes, this is coming up, and I think it will be a future of the energy. Because see, now the sources where you are using, say, hydrogen. Hydrogen is one of the right green fuels. But when you combust it, you get that. Similar thing is with ammonia also. If you are able to use this, it's a good storage of that. But now the question comes that, see, people are talking about urea also, because the same thing is with urea also. The question is that again you need some source of hydrogen for storage of the production of the ammonia and then storage. Presently, most of the ammonia which is consumed by the fertilizer industry that comes from the natural gas, right? And coal-based fertilizer plants, right? They are there say 50 years back and were shut down, and now because India has plenty of coal, again this FCI Ramagundam they have initiated this coal gasification followed by again for the synthesis of this kind of fertilizer. So ammonia is will come in future as a storage of hydrogen source, because you need to look at the if you don't have the good source for hydrogen storage, then ammonia could be one, urea could be another, like those kind of energy storage. This will come up.
Okay, so
1 minute final remark.
do you want to say something?
I think you can give 1 minute.
Yeah. So our time is almost over for this particular session. So I would request our panelists to give some final remarks for this session, maybe 1 minute each.
I have a last question. There was why you got for the resource. I was competent to respond to that. What exactly is quantity or resource of coal available with us? Like with the requirement of energy security in our country and like the projected requirement. How much coal do we exactly for how many years can it last?
See, as I said in my presentation also, the proven coal reserves presently are around 160 billion tons, right? And if you look at total that's calculated from the geothermal analysis, around 240 or even more than 240 billion tons. And this will last more than 100 years if this is so, because see, the sources are available in India. The only thing that when you look at the utilization of this kind of grade of coal, because high ash, so India is still importing, despite that India is still importing a large amount of coal for the gasification. So more than 35% of the coal is being imported for the gasification. The reason is that the quality of the Indian coal is not very good, and the gasified design is a challenge to utilize this high ash coal. 20% ash coal gasification is very easy, and ability bed gasifiers can be used very easily. But when you talk about 40% ash gasification of this coal, right, you have 60% is the coal material, 40% is the ash, which will form the clinker if you use the temperature of 1000 degrees centigrade. So low temperature gasification, ability bed will not be good for this, because everything will go away with the in the form of fly ash. So there are a lot of challenges with that kind of high ash coal. So if we are able to utilize, that's what the oxy, steam, those kind of gasification, and at a lower temperature, say around 750 degrees centigrade temperature, then there are your ash will come at the bottom. You collect that, use it for the fly ash. But fly ash can be used for catalyst, for other compounds. Then I think that there are the methods of solution for this. So Indian grade coal gasification, that is a challenge. And that's why the fluoride bed gasifier or bubbling bed gasifier, if these come up, I think that will solve the problem. And still only so far the Simple is working, Thermex is working, and the BHEL, they have developed a 0.5 TPD of this kind of highest coal gasification plant. But the commercialization is yet to be done.
You can make the or quick summary for the
So from my side, whatever we have discussed, the improving the efficiency of the existing systems is again a very important thing to be taken up. And whatever systems we have, the coming up with the new systems will have its own implications. There is economics involved in it, and the power sector is a capital intensive sector. So theoretical studies should be carried out for finding out these sources of inefficiency, eliminating them through energy analysis as well as through XLD economic analysis.
Yeah, I agree. I think most of the things have already been said. The major challenge in the gasification design, right, is how to bring down the cost of this gasifier, right, and high efficiency gasifier. So 90% efficiency, coal gasification efficiency is available, but we have to reach to a level of 95%. And as I said, the energy, where from the right for gasification, how much energy, so low energy, and the most important thing is that can we go with the plasma gasifiers, right? That could also be a new area of research. And look at the plasma gasification system with thorough XLG analysis, reduced unit operations within the system, and the coal to hydrogen, right, or coal to syngas and coal to hydrogen. I think these will be the vision for the future, where we need to work hard that how the maximum hydrogen can be produced from the high ash coal, right, and at an economic way, right. That's very important. That cost should be at its minimum for the production of hydrogen from the coal. Otherwise, like coal to methanol, already China has lot of right methanol available at a rate of 25 rupees a liter. But in India, if you want to develop this kind of technology, then it is very important that we should right produce the methanol at a rate even less than that, say 22 rupees per liter, and which is a challenge. We need to face these kind of right problems and look at R&D activities and decades. Thank you.
If I look through the telescope, I see hydrogen is a distant dream, but we can't stop working on hydrogen. If you have to apply hydrogen to vehicles, you can depend on fuel cell, of course, but fuel cell cannot give pulses of energy or high power suddenly. So you need a battery. You need a battery to go with it. So it's a distant dream. So in the meantime, I think we should work on cleaner fuels and less emitting engines that satisfy the standards. I think hydrogen will be another 30 years from today.
Previous speakers have summarized it well. So I would like to add a few things that apart from the gasification, we also need to look into how to integrate the gasifier with the existing power unit system. For example, if I want to use the gas turbines or the fuel cell, I need to clean the syngas to a certain extent. Okay, I need to remove tar and other chemicals from this, and then it can be introduced. So research has to be directed in that direction. Professor Pant said plasma gasification, but I personally feel that if we can use plasma upgradation of the syngas, that can be one of the approach which will be probably less expensive compared to the plasma gasification itself. And thirdly, I would like to summarize that we have to come up with the innovative cycle design for the power cycle design. For example, the combined cycle is there, but can we explore more by various other combinations? Okay, fuel cell, solid oxide fuel cell that gives a very good efficiency, and it can be probably it has to be looked into the future how it can be useful for this purpose. And yeah, so these are basically another approach what Professor Agarwal mentioned about the solar. Yes, so solar and the biomass can go parallel. So we can have the solar thermal power plants, and during the when the sun is not there, that time we can have the biomass gasification and we can sustain the plant. So it will be a combined cycle operation with thermal energy storage, etc. Then So those type of innovative things we need to think about for our better future. Thank you.
Okay, for our next speakers,
Dr. Pachikulo?
Yeah.
Yeah.
Okay, just to add my global context, it's a very interesting questions and few 1 minute summaries my panel colleagues has given. In terms of, to start with the gasification, yes, in the global context, we have an experience in terms of doing co-firing the gasification approaches, and we've done several activities with the UK context as well as in China. Up to certain percentage, we can do that without major changes into the system. Coming to the solar side, yes, there are several European projects is running mainly for the carbon capture point of view, in particularly because that is an endothermic process. You need a large amount of energy needed. The solar assisted one is helping to improve the economics point of view and energy management. The similar approaches we can try for the gasification, but it is not economically feasible as CSP technologies is highly concentrated and you need a large amount of space, and the solar is not an attractive option. However, if it comes to the combustion, like integrated approaches, people were doing in a way that China, if you talk about a couple of years back, they were building a huge number of coal-based power plants. Now they are saturated. The usage of those coal plants is more or less like a 50%. To increase the life of that coal plants, they were talking about solar assisted coal plants to meet the reduction targets point of view, as well as all the components can be shared approach. That way the economics will be benefited. People are talking about integrated solar coal fire plants as well as gas plants as well. Coming to the UK point of view, when we started rolling out, phasing out the coal, the first approach we followed is co-firing, and then to the natural gas one, because gas-based plants tend to be more efficient than coal plants, because as we know that it is less cleanup is required and high efficiency, so to meet the overall carbon emissions point of view. The technology is there, and we can easily transfer. To end with, the main approach we need to consider is how to transfer these technologies. Where are these opportunities? Can we explore the technology transfer programs to the India and other global developing countries?
Professor Doctor, very quick summary from your side.
Very briefly, I would like to point out that India being an agro-based country, biomass can have great potential in the power sector, particularly to arrest the carbon level in the atmosphere and for global sustainability. And the government of India has rightly taken policy in this regard. But implementation of the policy required bridging of several technical issues. And this requires hand-holding between industry and academia and R&D organization. Coming to the solar aspect, solar energy can be utilized in several ways in the existing power plants. For example, solar energy can be used for drying of coal. That is one very important issue for which the power plants are apprehensive of using biomass, because they have to use high temperature in the mill in order to dry the coal, and they think that can cause fire within the mill due to ignition of volatile matter in biomass. So solar energy can be useful in doing that. Solar energy can be used to do the feed water heating. So that also will help in increasing the power output. So these are the innovative ways in which solar energy can be utilized in the coal-based thermal power plants as well, and which will be helpful. So this is my brief summary from my side.
I received one online question. That is, can we make very small gasifier to substitute the stove, the cooking stove, the chulha, the cooking stove, the chulha. So,
See, biomass-based cooking stoves are already available and they have already been developed now. But coal-based cooking stoves, is not based on what we say gasification based, right? It's a combustion based basically. And you need not to work for this, right? Gasification for the domestic level, right? Because the kind of design, the kind of, but the combustion, because you need power and a controlled power without any right pollution. So that way the combustion is the best because you are completely converting into the energy there, and that's what is the need at the domestic level. So I don't think that we should go with the gasification.
Okay. On behalf of the moderators, I thank all our panel members for a very lively discussion, and to the audience also for raising the questions. So, Aditya, do you want to supplement anything? Please unmute yourself.
No, thank you. No, this was really great. Thank you, all the panelists and the audience. I think we can move on to the presentations now. We have about half an hour for that. Hello?
Contributory paper session.
Can you hear me?
Yes, yes.
Okay. So we are moving on to the contributed papers, right?
Yes, sir. We'll be playing videos of all the virtual participants. I request all the virtual participants whose paper is being presented, please raise your hand so that we will let you on stage. Then you can unmute yourself and ask questions. Sorry. Sir, are we audible now? Hello. Can any of the panelists are audible or not? Hello.
Yeah, we can hear you well.
Okay.
Greetings to all of you. I am here to present my work on parametric study of combined solar and biomass-based power and hydrogen generation system. We are interested in gasification because gasification itself reduces CO2 emission, and end result from gasification is syngas, which directly can be used as a fuel. Biomass combined with solar energy is having great potential. It can be explored. And why we are interested in hydrogen generation? Because intermittency in renewable based plants demands energy storage, and hydrogen can be used as an energy storage. So that's why we are interested in hydrogen generation. Versatility of hydrogen is very good because we can also use as a raw material in pharmaceuticals and as a heat generation in different industries. So in this proposed layout, we are going to concentrate our solar energy at a central receiver, and then we are going to use molten salt heat exchanger to heat the air, and then heated air is going to perform gasification in gasifier. So the end results in gas can be stored at a particular temperature and pressure, and that is going to be used in a gas power cycle. And at the end of the turbine, we are going to have a large amount of heat, which is going to be used for hydrogen generation. For parametric studies, we have four different equivalence ratio at which we have different in gas composition, and we study its effect on four different cycle pressure ratios and four different turbine inlet temperatures. Efficiency increases as equivalence ratio increases as turbine inlet temperature increases, and work done also increases as equivalence ratio increases and turbine inlet temperature increases. At different equivalence ratio, the quality of syngas changes, and that's why the lower calorific value of syngas changes, and which result in difference of mass flow rate at the combustion. That's why we are getting difference in efficiencies and difference in work done. And the heat from exhaust can be used for hydrogen production. There are two possibilities. Either we can use steam reforming, and later we can use carbon sequestration to capture the carbon, or another possibility is simply we can heat water and electrolyze it at high temperature to generate hydrogen. Thank you for giving me this opportunity.
Ayush, can you give us some idea about the cost of hydrogen production?
Sir, at right now, I have no idea about cost of the hydrogen production.
Okay, so you have done the analysis of the overall plant, and what is the efficiency that you are getting?
So efficiency is about it's varying from 30% to 40%, in the range of 30% to 40% at the different
Right.
equivalence ratios.
Okay. Thank you. Thank you.
Go to the next one. Thank you, Ayush.
Pulsing MS Research. Greetings everyone. I'm the Pulsing MS Research Scholar at IIT Mandi. The topic of my presentation is exploration of organic Rankine cycle technology for low temperature waste heat recovery from engine. Motivation behind the study is that owing to the structure of IC engine, it has only an efficiency in range of 30 to 40%, so around 2/3 of the fuel energy is being wasted. So in order to balance the efficiency and for better fuel economy, engine coolant waste heat recovery using organic Rankine cycle technology is taken up in the present study. So this shows the schematic diagram of basic ORC unit with and for practical implementation of such a cycle, there are certain challenges that need to be addressed, for which dry working fluid R245FA is taken up in the present study, and due to the low space availability, so rather than going for pre-available evaporators, these are designed particularly for this application. So this is the methodology for designing part of shell and tube as well as plate type heat exchanger. So initially primary experimentation was done and heat balance was done to obtain the heat load available with the engine coolant, and owing to the low space constraint, firstly the shell diameter and tube diameter are predicted, and similarly plate width and plate thickness are predicted initially, and then iterative process value to obtain the desired heat output for the optimum pitch, and similarly the iteration is done on the compressed plate pack length to obtain the optimum configuration for the particular heat load. These are the results obtained for one particular heat load, that is 7 kilowatt heat recovery from engine coolant for one particular evaporation temperature, for as well as latent heating part. These are the design points for shell and tube as well as plate type heat exchanger, and similarly can be load and evaporation temperatures. So this is the network output to heat transfer area as the indicator, which gives us the idea at where we should operate and what we gain and what we have to provide for the implementation of such a cycle with evaporation temperature. And for the proof of the concept, numerical investigation was done through 3D modeling of the evaporators, and shows good agreement with the analytical results. So concluding the study, engine coolant is significant potential for waste heat recovery from the recovery of low temperature waste heat recovery, and plate type heat exchanger further provides us the compactness, and these are the Thank you.
Okay. Thank you, Inderpal Singh. Are there any questions from the audience? Inderpal, the last slide you showed some numerical simulations. Can you tell us the dimensions there?
Yes, for the shell and tube heat exchanger, the shell diameter of 1/2 foot, and for sensible heating part, the 1/2 meter length of tubes was taken up for the study, and for plate type heat exchanger, the dimensions for the width and height are 127 and 90 mm.
Okay. Are there any further optimization of the heat exchanger possible? Was this included in the study?
No, sir, these one are optimized. Then further this process can be further taken up for varying load of engine coolant, and we can see how a single particular optimum for one particular heat exchanger behaves for other varying heat load conditions.
Okay, so you have also optimized the heat exchanger for a given set of conditions.
Yes, sir. This is optimized one for a given set of heat load and temperature, coolant temperature, by varying the pitch to diameter in a range of 1.2 to 3, which is by the literature an optimum range of varying PT by D naught value.
All right, thank you. Any other questions from the audience present at the conference? If not, we can move on to the next contributor talk. I cannot hear you, Sam. Now I can. Yes, we can move to the next speaker, please.
Good afternoon, everyone. Myself Tejas Pai. I'm here to present a small part of my research work, which is entitled as Greener Route for the Transformation of Bioglycerol to Glycerol Carbonate using Lithium-Based Heterogeneous Catalyst. First of all, about biodiesel. It is an alternative conventional fuel. During production of biodiesel, one can see glycerol is produced as a main byproduct, which can be seen in the large surplus. This large surplus can be either eliminated or could be reused to minimize the biodiesel production. Therefore, for the sustainability in the biodiesel production, the evaluation of glycerol to different value-added products is an essential. Because of having this wide variety of application which is shown here, the glycerol is known as a functional molecule of conversion to different valuable products like propene 1,3-diol, glycerol, acrolein, etc. Among them, my work is based on the conversion of glycerol to glycerol carbonate using heterogeneous catalyst. These are the objectives of the presentation. First of all, I designed a lithium and titanium-based heterogeneous catalyst in which titanium oxide is used as a support and lithium is used as an active metal over there. The process followed is a simple wet confirmation method which is shown in this slide. The physicochemical properties of the catalyst is through TGA, PSA, the exposure and metaforming studies. Uh, the formation of the formation of the single phase molecule is confirmed through the XRD pattern, but lithium peaks are not observed in this, which is further confirmed through the XPS spectra, in which the lithium peaks are observed from 0 to 100 electron volt of binding energy, and the oxidation state of different elements are confirmed to the XPS spectra. The catalyst is having a spherical morphology in which lithium impregnation is confirmed to the HR image of the HR plane studies, and the average particle size obtained is 50 around 50 nanometer. After this, the catalyst is undergone for the transesterification process in which glycerol reacts with DMC to form the glycerol carbonate. The basic nature of the catalyst is helpful in the deprotonation of the glycerol molecule, which undergone for the to react with the carbonyl carbon of DMC that further undergone cyclization to form the glycerol carbonate. The synthesized product conforms to the 113 CNMR spectroscopy. After this, the optimization of different reaction parameters are also done, and with which the maximum conversion obtained is 95% and 91% of the glycerol carbonate yield with 99% of the selectivity towards glycerol carbonate. The reusability of the synthesized catalyst is also checked, which found that the catalyst is recyclable up to 5 reactions. Therefore, it can be concluded that the synthesized catalyst is appropriate for the glycerol carbonate production. Thank you.
Okay, so it's a good presentation. Can you tell that what is the substitute for lithium, because lithium availability will be an issue and you are using a large amount of lithium in the catalyst.
Sir, I use lithium because it is highly reactive towards the deprotonation of the glycerol. And for substitute, we can use the magnesium. So for substitute, we can use magnesium oxide or sodium, but we have to use it in very lesser amount because because for the formation of glycerol carbonate, we want a moderate basic size. Because if it is highly basic, then it converts the glycerol carbonate to glycerol. Because with a high basicity converts the decarboxylation of the glycerol carbonate, which forms glycerol. So therefore, it's not a only single product is formed. This is the major drawback. So that's why, sir, I use a lesser basic, which only used for the deprotonation of glycerol, which further react with dimethyl carbonate and lastly forms glycerol carbonate with the 99% of the selectivity only towards the glycerol carbonate. Thank you so much.
Hello everyone, I am Amol Nivalkar, working as a project associate in CSIR near Nagpur, giving a presentation on ensuring green energy transition using circular economy framework, a case study for Delhi. Accompanying rapid resource depletion and the negative effects of climate change, the adoption of circular economic strategies in the environmental sector is gaining global recognition and application. In comparison to the other Indian cities, Delhi has the highest rate of electricity usage. According to the Environmental Performance Index, Delhi is one of the world's most polluted megacity. And according to the CPCB, that is Central Pollution Control Board, Delhi is surrounded by extreme pollutive industrial zone that surpass the limit of air pollution. So that's why it is become necessary to study over Delhi zone. The purpose of this study is to examine the energy demand and emission generated by sectors such as industry, transportation, and others for Delhi in the upcoming years by implementing and comparing scenarios such as circular economy and pandemic. The three sectors, that is built-in area, transportation, and industry, are chosen because it has a significant energy consumption in Delhi. LEAP, that is low emission analysis platform software application, is used to analyze the emission reduction of economies and industries in the energy system assessment. Business as usual, circular economy, and pandemic were the three scenarios implemented and examined for the energy projection and its emissions. Circular economy is implemented in such a way that Delhi's energy demand is reduced by applying resolve framework. And the effects of the COVID-19 pandemic on Delhi's energy track are represented in the pandemic scenario. It was seen that if a pandemic scenario is considered as opportunity in terms of environmental perspective, the reduction is much higher than a business as usual scenario. But technically, it is not possible because it cannot exist for the longer time. So, circular economy can be the best fitted scenario for the reduction of respective energy demands and emissions. When comparing the circular economy and business as usual scenario, this figure shows how much each sector might contribute to Delhi's green energy transition. As we can see from this Sankey diagram, the public transport and freight play a vital role in saving in final energy, CO2 and PM2.5 emissions. This study examines the sustainable energy transition alternatives and results for Delhi for a defined number of years from 2020 to 2040. In comparison to BAU, the improved saving in final energy consumption, CO2 and PM2.5 emissions could be 45, 41 and 30%. Delhi City might save 40% of energy and 35 to 55% of CO2 and PM2.5 emissions by treating pandemic as an opportunity for the year 2040 as compared to the circular economy scenario. This study might be expanded to include a wider range of sectors with the result assisting policymakers and the government in implementing new policies to move towards the renewable energy and green fuels. Thank you all.
Hello everyone, I'm Aditi Parihar with my colleague Shruti Patnaik from Maulana Azad National Institute of Technology. I'll be presenting on the topic Assessment of Noise Pollution Level, a case study of Mumbai, India. So the exception of land pollution And noise pollution cannot be seen with bare eyes. It has comparably unsettling and as well as detrimental effect on everyone and environment. Urban areas have become more reliant on man-made components as technology and engineering have advanced, and all these contributes to noise pollution that has now reached to dangerous proportions. The motivation of this study lies in providing mitigation measures of noise pollution, which which are usually tackled at a larger scale with high-scale infrastructure, whereas noise pollution has its most impact on neighborhood level, usually in areas which sustain a mixed land use. So the purpose of this research is to estimate the level of noise pollution in mixed land use area in Mumbai and to develop an ecologically sustainable technological landscape that is creative and green in nature. The study is carried out for different land uses, that is residential, commercial and open spaces, depicting three main types of road that are arterial, subarterial and local road at different times of day like morning, afternoon, evening and night. The readings in terms of average decibel, maximum decibel and minimum decibel were recorded and tabulated as graphs for better understanding. A survey was conducted in order to analyze the perception of people towards noise pollution, and the detailed methodology chart is shown here. Here we have the findings from the survey along with graphs and images of the area. The data was studied and it was found that the values exceeded the Central Pollution Control Board, that is CPCB specification for residential and commercial sector. The condition needs immediate action as the outdoor noise being generated by man-made activities are high when residential land use is taken into consideration. Further, respondents believe that they experienced more noise pollution before pandemic and the situation is much better due to pandemic. It should be noted that the present situation seems to be better, is already far more harmful than the standards prescribed by the CPC. So the study assesses the noise pollution levels in mixed land use area, taking into account the impact of noise pollution and the standards that have been set. The paper presents a specific purpose since it is based on mixed land use area at neighborhood scale. People may reduce the noise pollution by turning off appliances when not in use and many more. It proposes unique noise reduction strategies that may be implemented at neighborhood level and do not need large scale infrastructure expenditures or extensive organizational engagement. Thank you.
Thank you for your talk. So can you please tell me that how did you measure the noise and do you have any noise map of Mumbai? Particularly, I'm interested whether it varies from location to location. For example, residential to the industrial and commercial areas. Please unmute yourself.
Sorry, sir, can you pardon once again? It was not audible.
There are two parts. Can you tell me about how did you measure the noise? And is there any database available about the noise level at different regions? For example, residential versus commercial versus industrial. So can you tell me about the source of this noise pollutions?
Yes, sir. Actually, we had a survey done. So we used the Genesis app on phone and we did the survey through that.
Thank you.
Hello, this is Saurabh Gupta. I am speaking on behalf of Combustion Energy Conversion System Laboratory from Mechanical Engineering Department, IIT Kanpur. I will be presenting my work, that is an experimental investigation of highest coal gasification and pilot scale bubbling fluid isotope. Indian power sector dependency on coal is not new. We have currently fifth largest coal reserves, standing at 344 billion tons in 2020. India has a coal feedstock with a low grade quality with the highest content above than 30%, and currently we have coal reduction technology, that is subcritical steam cycle based pulverized coal power plant, combustion power plant. But the problem with this kind of technology is that it has a low efficiency as well as it emit carbon emissions. So coal gasification can be an attractive technology in with regard to, and gasification converts solid carbonaceous fuel such as coal into a combustible mixture of gases, that is called syngas. It contains majorly hydrogen, carbon monoxide, and heat. Among all coal gasifiers, fluidized bed gasifier seems to be suitable choice for this kind of coal with highest content because it operates temperature at a temperature less than ash fusion temperature. So we tested the performance of Indian highest coal with the highest content above than 45% at a different equivalence ratios, and we have to steam to coal ratios on the performance evaluation for parameters such as carbon conversion efficiency, coal gas efficiency, and higher heating value. So this is the test metric for which experiments were conducted. We tried thermal power of 380 kilowatt, and we varied equivalence ratio between the value of 0.19 to 0.28, whereas we varied steam to coal ratio between 0 to 0.2. You could see from temperature plots that we achieved a stable autothermal gasification operation because temperature becomes constant at a particular value of equivalence ratio as well as steam ratio. So from these plots, it is clear that with an increase in equivalence ratio, higher heating value decreases, whereas carbon conversion as well as coal gas efficiency increases. On the other hand, with an increase in steam to coal ratio, higher heating value increases, as well as carbon conversion as well as coal gas efficiency increases. It is a benchmarking with the previous coal gasification experiments, and it shows that our experiments performed really well in comparison to that. We found agglomeration tendency also with this type of coal. And while doing a CMETS analysis of coal agglomerate samples, we found that the major reason behind the agglomeration was the generation of local hotspots, not because of alkali metal content. So these are the conclusion. We found a stable autothermal operation of BFD gasifier above the fluoridation number of 2.3, whereas we found highest high heating value of syngas as 3 megajoule per meter cube at equivalence ratio of 0.25 and steam to coal ratio of 0.19.
Hello, Sam. Is someone speaking there? I'm unable to hear anything this side.
Professor Aditya Saurabh, can you hear me?
I can hear you now. So, well, yeah. Can you hear anyone from the conference?
No. I can hear you only. I cannot hear anyone.
Same
We cannot hear anyone from the conference.
I see. Okay, there must be a disconnect from their side. I will quickly check.
If
Yes.
I'm correct, all presentations is done. Is that maybe Sam might have disconnected?
No, he should not have disconnected. I think there would be a concluding part at the end.
Oh, is it? Okay.
I will quickly check with him if there is a problem. In the meanwhile, if you, Professor Pachigula or Professor Datta, if you have any questions to Saurabh, while I'm checking what is happening there.
Question to whom?
To Saurabh Gupta, the presenter, the last presenter. Yeah.
Dr. Pachagula, in UK,
Yeah.
What percentage of biomass share are you using in the coal-fired power stations?
We tried up to 20% without changing
20%.
anything, burners or anything.
Without changing anything. What is
Yeah,
the coal composition? I mean, how much moisture does the coal have? Do you how much I mean heating of coal is required in the mill? Because here in India, I discussed the matter with several power plant people, and they say that they are quite apprehensive about mill fire if they use simultaneously biomass with coal, maintaining the required temperature. I don't know. Probably we have been connected. So
Yeah, means the issue with the coals, yes, we do get some moisture content, but we usually treat them and put them into the silos so that the moisture is not gone into the coal. In terms of the biomass, yes, we do pre-treat that. Up to 14-15% is acceptable, and mixing it into the coal one. But the approaches we started doing is like you guys as well, same thing, using the pellets and remill them and use it for the firing purpose. Pellets you can manufacture only up to like 14 to 15% or maybe up to 20 as well. So the moisture is already managed for the biomass point of view. Then you can mix it with coal, pulverized one, easily.
I understand.
Yeah.
Just for information, I think the conference is able to hear this discussion, but we are unable to receive anything from their side.
Okay.
And they are closing the session. So what I can do is thank the online panel members and speakers personally. Thanks a lot for joining and the presentations. It was really a great session, I think. And with that, I think we can just disconnect. I don't know what is happening on their side, but they are also closing physically.
Okay. Thank you very much.
Thank you.
Thanks to the
Yeah.
organizers.
Bye.
And what we have to do with this evaluation sheet? Should I send it to Professor
Yes, we
Sen
can
or?
send it back to the person who shared it, or you can just put it in this session 3A WhatsApp group. Either of this would work, I think.
Okay.
Yeah. Yeah.
Okay. Thank you.
Okay.
Yeah.
Thank you.
Thank
Bye.
you for this nice
Bye.
session. Bye. Yes.
सैम सफाई हो गया